Hello, everybody, and welcome to the third lecture of Econometrics for Data Science, where we will be talking about the least squares, or just least squares. Later, we're going to talk a little bit more about the least squares estimator, although we're going to move in that direction today. At the very end of the day, I'm going to mention something about overfitting and underfitting, which is sort of related to least squares and obviously comes up in data science a lot. I assume you've seen something like that before, possibly. Um, Great, excellent work on the first Colab assignment. Please check out the comments that I left for you. Overall, it was quite nice. That one, of course, we're like learning about, you learned a little bit about the types of comments that I leave, the things I emphasize. So I hope that was useful. I will continue to leave comments. And please don't hesitate to reach out to me before the homework is due. I'm happy to answer questions, clarifying questions, meet if I'm available. So yeah, continue the good work on that. Let's jump into least squares. One thing I want to mention right at the beginning, there's least squares and then there's ordinary least squares. There's also things like weighted least squares and generalized least squares. So least squares, what we're covering today, covers something more meta than ordinary least squares, for example. That's a specific type and the most common type of least squares, but that is not the only thing we're talking about today, because the things that we are talking about today will also apply to more complicated least squares type models. So let's go ahead and get into it. Hopefully we're getting a little bit more used to the matrix type math if you haven't seen that before. But last time we pointed out that we could write a regression model this way in matrix form. And then these would be what those matrices look like. I asked you about the X beta matrix when you actually made that calculation and what that would look like. Kind of just get some of that matrix algebra blood flowing, because probably that's one of the things that's more likely to be new to a lot of you, but it's very useful to sort of just get used to thinking about those things in that way. We're going to get a little bit more heavy on that today. If that's giving you any trouble, just don't hesitate to reach out to me. So we could think of this as the population regression relationship that we're making. If we're even thinking about this, we're making an assumption about some system in the world or relationship in the world that's linear and saying, maybe I'll think about regression. And so the second we start thinking about regression, we're imposing some type of assumption of linearity with the flexibility discussed in the last lecture, of course, where we can have tons of nonlinear flexibility within that linear regression model. So the population parameters of this model that we're interested in estimating often are the beta coefficients, which we discussed quite a bit last time. Sigma squared, which is the variance of the error terms, and then we can get a bunch of other stuff from the variance of the error terms. And the error terms themselves are population parameters to be estimated. Those are going to be tricky to estimate because we're going to have a lot of things to estimate with error terms relative to the amount of data we have always. Because notice that like this matrix or this vector and this vector are the same size. So in general, we have one piece of data per error term. So estimating the error terms becomes a difficult process as a result of not having that much information for each individual error term. So oftentimes that amounts to estimating things like the distribution of the error terms and things like that. So let's consider, so the sample counter, once we come up with our estimates in general, we'll call those B, although beta hat is quite common. S squared, although also sigma hat is quite common in different situations or honestly just among different people. And then E we'll generally use for what we call the residuals, which are the sample error terms. So the term residual literally means the sample error terms because the error terms are population parameters. So let's think about our goal for a second now, because probably if we haven't mentioned this by even starting to talk about regression, we think that there's a linear relationship going on. Probably we want to try to estimate that linear relationship. So the first thing is essentially coming up with criteria. What criteria should we use if we're going to estimate the relationship between one X and one Y? So we're estimating a line essentially. What criteria are we going to use to choose between two lines? Like, why is line A better than line B? Because we could use different criteria. The term least squares refers to a body of criteria, and that's why it's more meta, because we use the least squares criteria in ordinary least squares. We also use the least squares criteria in weighted least squares. So the terminology least squares refers to the criteria that we will now cover. So we want to estimate our beta, our coefficient parameters, such that we are choosing B, right? We get to choose what our estimate is, because there's many different estimates we might choose of beta. So we want to choose one. And this least squares mean we're going to choose that to minimize E. The residuals are a vector of residuals. So E transpose E, which, by the way, I can solve. I mean, you can think of it this way. This, in the sample version, this is Y equals XB plus E, and we could solve that for E, right? We could leave E alone on one side of the equation. And then that solution would be Y minus XB. And so E transpose is the same thing as Y minus XB transpose. So all I'm doing across this equality is substituting the fact that the error is defined as the actual value of Y minus my estimate of the value of Y that I get by weighting my independent variables linearly and then getting out an estimate of Y. So this is the error term both intuitively and from math. And so these two sides of this equation are the same. I'm being a little bit fast and loose because I didn't bring over my minimum. So by the equality, I'm just referring to the E prime E. Now we can expand this to find that it's equal to this. And then simply note that this E, so if we want to see what this thing looks like for individual values for a multiple regression, the first error term would be the first Y value minus this intercept estimate minus the slope estimate of the first X value independent variable times the first value of the first independent variable, and so on down to K independent variables. So that's simply what this E matrix looks like. And then that's sort of this, or sorry, vector looks like this is what one of the terms in this vector looks like after we make that substitution. And then now we can see, we can also expand what E prime E looks like. So we know that vector is just E1, E2, E3 down to the line to N, our number of observations. And then if I did the matrix algebra on that, it's literally just E1 squared plus E2 squared plus E3 squared plus E4 squared. So that's the sum of squared errors. So what this really says is I'm choosing my estimate B to minimize the sum of squared error terms. Now that gives us a lot of nice characteristics, like if I didn't square them, some of them would be negative and some of them would be positive. And in fact, I would just get zero out of that. Because in a second, we're going to show that if you just add up all the error terms, you should get zero if you use least squares to make your estimates. So no, that is just going to be true in the population regression too. So that's a nice characteristic. Another characteristic that intuitively people like is if you have big errors, they're punished more because you have an exponential function in the error, basically. You're squaring it. So those are a couple of just nice, really quick, intuitively meaningful and possibly beneficial parameters we would like. We could use least absolute value criteria. That would be another option. So least squares, that meta thing, that lives under that ordinary least squares, weighted least squares, we could say, no, instead of squaring the error term, I'm going to take the absolute value of every error term and then add those up. That would solve the adding positive and negative errors together problem. It would not punish the extreme values. There might be good reasons that you don't want to do that. That would be a different type of criteria. So an important thing to recognize is that we're just going into a certain type of criteria we're using to make estimates. So let's just take a look at some charts of what this looks like. So this is just showing, look, we could, if we had a scatter plot for simple linear regression, there's many different lines we might draw and be like, why not this line? This looks pretty good. And then we can see what the slopes of these different lines are. And then we can apply that least, because we can calculate error terms, the difference between the line, the vertical difference between the line and the point from the sample for any line. And so if we do that, then we can square those errors for any line and add them up. And then we can basically look at, okay, based on the slope that we choose, because that's our choice. We get to choose our estimate. Of course, we want to make a good choice, but we're allowed to choose whatever estimate we want. So this just simply shows you how by choosing the least squares estimate, which I calculated up here, we do indeed minimize our criteria, the sum of squared errors. And so this is just a graphical showing what's happening here. If we use the least squares criteria, that means we're going to choose the line or choose the setup, the relationships for the hyperplane for multiple regression or whatever. That minimizes this value. This just shows for linear regression, simple linear regression. Here's the best line right here. And then we see that, yes, indeed, that line's slope is where the criteria is minimized. So that's fundamentally what's happening in the background. So then, of course, we can solve this minimization problem analytically because you can go to a statistics textbook and for like simple linear regression, just see B equals this function of the data. And so that means we have a closed form solution for least squares. And so this math just shows how we get to that. And it's some matrix calculus. So maybe you probably haven't seen that before, or maybe you haven't seen that before. So I thought it was a good time just to show you this is how statisticians would show, okay, now I've determined that I want to use the least squares criteria. As you most likely know from calculus, if we have a maximization or a minimization problem, we can use calculus, differential calculus, to solve that problem. So if we take the derivative of what we're trying to minimize with respect to our choice variable, B, and set that equal to 0, we should either be at a maximum or a minimum. We can use that to show that this is in fact the solution to B, and this is a formula we will refer to regularly in this class, x prime x inverse x prime y. So like that's just in your brain all the time if you do regression a lot. That is the matrix form of the solution to the least squares problem. And then we can check, is this a minimum or a maximum, using a second order condition, which requires us to take the second derivative of our criteria with respect to our choice variable. And then this is what that looks like analytically. And then you could prove elsewhere, I'm not going to ask you to do this, but you could find a proof of this, that this does represent a minimum if X, our matrix of independent variables, is full rank. When is that matrix full rank? Intuitively, when the independent variables in it are not perfect linear functions of one another, which intuitively makes sense too, because if you step back and say like, I'm going to put one, so we talked about categorical variables last time. You could have a variable in your model called married and another variable called not married. If you tried to run a model like that, it would actually not work because those are perfect linear functions of one each other. And even more intuitively than the math side, what we're doing is like feeding information into a model and trying to get a good result, a good prediction from that model as a result of feeding information. If I feed it exactly the same information twice, that will not improve my result. Telling it who in my data is married and then telling it who in my data is not married is an example of giving it exactly the same information twice. And that's the mathematical way to talk about that, is essentially saying that the matrix is of full rank. So it's nice. It's in a sense, it's actually kind of beautiful that those mathematical truths line up with our intuitive feelings about these processes. And I think that in econometrics, that's one of these emphases that aligns with probably what I've emphasized in the previous videos as well. So now let's consider the bivariate. So two variables, one dependent, one independent, simple linear regression model. So let's have Y be undergraduate enrollment at Weber State and X be the Utah unemployment rate. And assume that the population regression equation looks like this. So I'm not writing that in matrix form this time. I'm writing it in individual observation, arbitrary observation form. And I'm looking at this thinking this is time series data. I'm also thinking equation is spelled wrong right here. But time, so in general, you'll often have time, T for time and I for individuals, S for states, things like that. Although annoyingly, I'm currently reviewing a paper that uses T for something else. And I'm like, dude, you're confusing me because T is for time. But in this case, you can assume in my class that if I use T, I'm using some type of time variable. And then, of course, I'm telling you that right here, capital T is the total number of observations instead of using capital N, because that makes clear I'm also talking about a time series data set. So then we can see, okay, what's the sum of squared errors? It looks like this. For the sample parameters, now I switch from population to sample right here, and then I solved for E to make that substitution like the one above. The squaring is essentially the same as the transposing above. Then we know we want to take the derivative of this criteria with respect to the intercept, because that's one of our parameters. We have two choice variables, B naught and B1, because up here we're being arbitrary and saying B, that could be K plus one choice variables. Here we have one independent variable, so K equals one plus an intercept. So that's the K plus one choice variable is one plus one. So that's why we need we have to write that equation out twice, just like in calculus. If you're solving a multivariate optimization problem, you need to set the derivative of each choice variable with respect, set the criteria with respect to each choice variable equal to 0. So that's what we're doing right here. We can rearrange those. These are called the normal equations. You can sort of suck some intuition out of these. Like if I add up all of the y's, then I should be able to add up all the intercepts and add up all the slopes times the independent variables, and those should be equal. Like that's kind of interesting to step back and think about. It does make sense that this is true. This one also makes sense, but is more complicated. Like sitting back and thinking about this one, it's going to be more complicated. And then we can solve this set of equations to show the solution to this which I think I asked you to do because I do not want to do that. Go from here, the normal equations, to here. So we see that the intercept, which I had to do in graduate school. So I'm just passing it on. I'm paying it forward. And it's a good thing. Like that good paying it forward movie. It's a positive thing. Paying it forward. B naught, the intercept is just the sample mean of the dependent variables minus the slope times the sample mean of the independent variables, which this tells us that the line goes through the sample means. Because there's no error right here, right? So that equation right there tells us that in regression under the least squares criteria, if we have an intercept, the line always goes through the sample means. Because these X bar and Y bar is like, you could think of that as an example of a point. And if you solve this for Y bar, you would see that this is a point on our line, where our line is defined by an intercept, B naught, and a slope, B1. And then B1 can be solved. This is the slope now. And I want you to think about way back in the day when it's like rise over run. One way to think about rise over run is how does the dependent variable vary with the independent variable divided by how much is the independent variable varying. Okay, I'm going to say that again. Rise over run. Run is like how much is X moving. Rise, because of the word dependence, implicitly means we're thinking about something that changes with the independent variable. So how to rise is how does Y change with X? So that's what's on the top of this, how Y and X co-vary together, how Y changes with X, how much X is changing around in the data, because now we're talking about random variables. When we were doing it in algebra in middle school or whatever, we were talking about purely deterministic stuff, but the intuition is exactly the same for this slope equation as it was when we were in middle school and we're talking about slopes. So that's really important because a lot of this class is about communicating about data science, and my biased opinion is that econometricians are really good about communicating about data science because of the areas that we focus on and what we focus on when we're doing data science. And I think stuff like that is useful because this is for a simple regression, but we could think about this in the context of multiple regression too, and it remains intuitive, just like this equation remains intuitive. It's just more complicated to suck the intuition out of it. So it's worth it to stop at those easy intuitive cases, make sure we got it so that we're prepared in those more complicated cases. Now we can get some interesting things out of the algebra of least squares. So consider the matrix first order condition, which we showed above. So basically what this shows is that if we have a constant or intercept term in the regression equation, and we've already mentioned the intuition about this above, then it must be true that the sum of errors equals 0. So this kind of points directly to what we were talking about before. You can't use the sum of the error terms as a criteria because it will always be 0. So that can't possibly be the criteria. And in part, we also like this because this means that if we divide by n, the average error is 0, right? Which is a nice characteristic to have out of regression. And so basically the conclusion of this is if we include a constant term in the regression, we get that the positive and negative errors will cancel each other out. You could also use this condition right here to show, as we already saw above, that it passes through the sample means. So this is another way to get to this idea right here that you could, so it's shortly, so let me back up and say it more carefully. You can use this condition, the fact that the error is summed to 0, to show that the line must go through the sample means. Finally, we can use the condition x prime e equals 0, which is right here from this algebra, because this is the error term right there, that the fitted values, so if we so the fitted values are once we make our estimates, and you probably know this already, but just to clarify, we have an estimated regression equation. Now we can put our independent variables into that estimated regression equation and come up with estimates of y, our dependent variable. Our estimate of y probably is not a real y value from our data, and we call that a fitted value. So those are the predicted values, and now we can say those are orthogonal to the originals. Now, intuitively, and this is a more complicated statement, but we're thinking about the fact that those are orthogonal or uncorrelated is another way to think about that, is that there's no overlapping statistical information between the errors and the dependent variables. Or so one, between the predicted dependent variables, two, or between the statistical model we're using, which is defined by B prime X right here, and the error terms. And so that means we've essentially sucked out all of the useful information into the model side, and all of the remaining that's in our, I should say, the useful statistical information in our data set. There may be other useful statistical information if we were to get more data, for example, but we've separated the useful statistical information from the not useful statistical information between the error terms and the fitted values, basically. Okay, now goodness of fit and analysis of variance. You probably all know what R squared is already. One of the most commonly referred to and probably also overemphasized things in data science and statistics and econometrics. But definitely less emphasis on it in econometrics, partially because of what are the goals, but partially because of, I think, of the way we think about what it means. Because if you chase goodness of fit as defined by things like R squared, you're going to have issues, as we're going to see in just a second. So, and this is also a good opportunity to talk a little bit more about matrix algebra and how it's useful to derive things and come up with new ideas in data science in places like regression. So we're thinking about our sample regression model right here. Now, notice that, so we're going to start by writing our regression in the deviations from a mean form. And before we can do that, we're going to define a useful matrix that we're going to call M naught. The first thing I want to say is that this matrix is arbitrarily defined to n. So this matrix is well defined for any data set of size n. It is not particular in any way to our particular data set that we're thinking about right now. So M naught is the identity matrix of size n. So an n by n matrix with ones down the middle, minus 1 over n times 2 unit matrices. It's unit vectors, sorry. And so basically, it would be useful for you guys to think about, you could write out what this matrix actually looks like and what this matrix actually looks like, and see that this is the resulting matrix that we get when we put those identity matrices and this unit matrix together, those unit vectors together. And then what's nice about that is that we can pre-multiply any matrix, any vector, I should say, by this useful matrix, and we get that vector in deviation from means form. So if we want y minus y bar, which is like y1 minus the sample mean of y, instead of just being y1 in our dependent variable matrix, now we have y1 minus y bar, y2 minus y bar, y3 minus y bar. So our vector of dependent variables is in deviation from a mean form. And that's what will happen if we pre-multiply a vector, any vector, by this useful matrix, is we get that vector in deviation from mean form. Now we can expand y to be the fitted values plus the residuals. And then notice that we just get e back when we pre-multiply that through, because what is the average of the residuals again? Because remember, this apparently E1, for example, is equal to E1 minus E bar, the mean of E. Why? Because the air terms add up to 0. So the average of the air terms is 0. So we just get E back right there. So the left-hand side of this vector is the deviations between y and y bar, and the right-hand side is the deviations between the fitted values y bar. So that's right here, right? These are the fitted values because they also have a mean. So sorry, no, that's in mean deviation from mean form because I still have MO right there. So those are the deviations between the fitted values and the sample mean. So true values in sample mean, fitted values in sample mean, plus the error term. So we still need the error term there still. So note that each of these sum to 0. So if you sum this to 0, or if you aggregate this or aggregate this, you get 0. So now we can pre-multiply this matrix by itself. And then, of course, we just get by the transpose of itself. And that's going to give us, and you could think about why this is, that's called the sum of squares total. So it will be like y minus y, it'll be like y1 minus y bar squared plus y2 minus y bar squared plus y3 minus y bar squared plus dot, 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 plus yn minus y bar squared. So this is called the sum of squares total. And I just described it in words, but I make sure you know what I mean by that description in words. And it would be useful to write out these vectors and convince yourself that it's equal to y1 minus y bar squared plus y2 minus y bar squared. And you've probably seen that. I mean, if you look up sum of squared total, sum of squared. Ooh, wiki. See, there it is. Y1 minus y bar squared plus y2 minus y bar squared. We are writing that this way. Those are the same thing right there. So that's SST, sum of squared total. That's a measure of the total variation in your dependent variable. Oftentimes, the thing you're interested in predicting, the thing you're interested in understanding the variation of. So this is another very useful piece of criteria. The total, this is a measure again of the total variation in your dependent variable. What this equation shows, I mean, this was an equation on the way, is that is equal to the total variation that you have explained by your model. That's what I have highlighted right now. The total variation in your dependent variable can be subdivided between the total variation explained by your model and the part of the variation that remains and is unexplained by your model. And this is obviously a useful criteria because now, first, we could never compare. Let me be careful about this. We could compare different models applied to the same data across different SSTs because we're holding enough constant. We could never compare across different samples, though, because we don't have a relative comparison. And that's why we do R squared. We take what I can explain and divide by the total. And that's why it's often a percentage, the percentage of what I've explained. If R squared is 0.85, my model explains 85% of the variation in the data. I bet you knew kind of probably from here to here. Maybe some of you knew the stuff above that, but now I want you to be way more confident in your discussion and thinking and using R squared, because now you know where it comes from. And now we can think about more complicated things like, what if I use weighted least squares? Then what does R squared mean? When we go into these more complicated least squares things, now we have a better fundamental idea of playing around with these ideas and these deviation from means ideas. We can be a lot more critical, think a lot more critically about what's happening in R squared in different contexts. Now, another possibly one that you use all the time, and one that comes out, I think, because of a huge focus on sort of like out of sample prediction and things like that, is a mean squared error. And that's great. It's very similar to R squared in a lot of ways. I'm not going to derive that or anything. It's just this. It's okay. Take what my guess was, y hat, compare it to what the actual value, square that, and take the average miss. So this is just the average squared miss in the data, basically. So I just want to look at something really quickly. This would be a bad model applied to the blue points. Why? Because the blue points appear to be nonlinear. We saw in the last lecture how we would fix this. So this is a linear fit on I simulated quadratic data to just show you. Let's do a linear fit on quadratic data and see that it's bad. We can still use regression for this because, as we showed in last time, we could just include x squared as a second variable in the model. But let's just look. So thinking about this goodness of fit criteria, so I've just printed two things I've done. One thing is I've just estimated this model in data. So I've taken a sample of data, estimated this model. But then I've taken the same underlying parameters, simulated new data, and then applied this model to that new data to test the out of sample fit. And I'm using the average, the MSE here. And so it's always going to be worse out of model, or I mean out of sample. So we see that here we get a bad fit in both. We get an average miss of 22 in sample, and then we get an average miss of 35 out of sample. So let's see what happens when we use the correct model. This is in sample, out of sample, and we get much better numbers, but still higher out of sample because I did not use the green points to select the data. I literally minimized the distance from the to select the parameters of the model. I literally used the blue points to choose the parameters of the model. So of course I get the best fit on that. It's in sample. Then when I go out of sample, I'm applying it to new data. Now this isn't bad. Now what we could do is be like, I want a better fit. And we could chase things like R squared or MSE. And I'm sure this is probably not the first time a lot of you guys have gotten this lesson. So I apologize for the redundancy if that's true. But some people, you'll see people do this. Like, look at how sweet this model is. This model like goes through most of the points. And it's true. This is a sweet in sample fit, 0.57 compared to 0.77. So percentage terms, I made a dramatic increase. I'm a dramatically better in sample model if all I care about is the MSE right here. However, now I'm back to being worse than the linear model out of sample. So that's called overfitting. It's what happens if we chase R squared and then apply, or MSE, and then apply our model. There's really good, of course, machine learning techniques to sort of balance the trade-off between better fit like this and overfitting but you need a lot of data to apply those things. So it's useful knowing this, even though some of those algorithms exist. Now, one thing I want you to just think about is stare at these graphs. What point is it? Because, like, honestly, if you look at this doesn't look like that bad of a fit compared to this. But there is one particular point that's causing this to blow out. And you can probably figure out which one it is. One thing that I want to mention is at the very beginning of the lecture, I talked about what our goal is matters. So you could be like, I gamble $100 on the same gamble every day. And so maximum ever, I'm going to lose $100 or I'm going to win $100. I'm going to double my money or lose my $100. Now, if you get a massive error term one day, you're going to lose that day, but you're still going to only lose $100. This number is being driven essentially by one massive error term. So you might like this model better in that world because the size of the error term is irrelevant to your criteria. On the other hand, you could be like, I'm running a company and my company depends very much on gasoline prices. And if I get an extreme error relative to my model, my expectation, that's going to be a massive problem. So the problem I have is proportional to the size of the error. Then this is going to be a really bad model for your criteria. So that is an intuitive, real way that we need to think about criteria. And it changes with every problem. And those are the types of ideas that I really want you guys to think about for this type of class. All right. It was fun to talk about least squares with you guys today. I will see you in the next video. Bye-bye. And I'm going to stop recording.